small volumes of strong acid, each containing 0.015 moles of hydronium ions, okay, are added to 1 liter samples of 2 basic buffers. All right, so I have 2 different ones. I should be thinking about this. I've got buffer A. So I'll just go ahead and I'll put an A here. My first buffer has 0.15 mole of diethylamine and 0.15 mole of its conjugate acid. All right, the first thing that you can notice about that is that since this says conjugate acid, then this is acting as a base. And they have the same amount, 0.15 mole between them. So if we think about what that means in terms of the Henderson-Hasselbalch equation, the concentration of the base and the acid are equal. This will be the logarithm of 1, which is 0. So the pH of buffer A before we add any of that strong acid is going to be the same thing as its pKa. All right, great. So we go and look for these. We have to go look for them in table A 5.3. And the values that are given to us are pKb values, not pKa values. So that's the first thing I have to do is I have to say, if the pKa for the diethylamine is 3.07, oh, wait, I want the pKa. Oh, that's right, I'm going to do this. If I've been given the pKb and I want the pKa, I'll subtract from 14, and then I will have that my pKa in this case is 10.93 because this was the one that we were told was 307. All right, so we have a pKa for it. What does that mean that I did? It means that what I did is I took diethylamine and the conjugate acid and essentially I flipped the whole thing. So my reaction is going to start with the acid, not the base. And what is that? Okay, they said it was diethylamine. Okay, and conjugate acid of diethylamine. All right. So that's an ethyl group. That's a diethyl on an amine. That has to be an acid. Whew, terrible. And water in equilibrium with the diethylamine. Okay, so that's back to the CH3, CH2, and there's 2 of those. And hydronium ions. Okay. Whew. Wow, just figuring that out is a major mess. But once you know what the formula is, it does make it a little bit easier. If you look up diethylamine and you realize that this is what it is, and then the other one has to be its conjugate acid, I'm going to have another H and a plus sign. So there's another H and a plus sign. And because I wanted a pKa, that meant I had to put the one that was the acid on the left in order to say it's a pKa. All right, so I've done all that. And if I look at the initial, okay, we know the initials, they're 0.150. I can just work with the moles because they're in the same amount of liquid. So there's my water, and then there's this. Well, it's small. We know it's small. We know it's really small because the pKa is almost 11. That's like 10 to the minus 11th. Yeah, really small compared to this. All right. Now we're finally in a position to add this small volume of strong acid. Okay, they're saying it's a small volume. Why did they bother to say that? Oh, they didn't want me to worry about doing this in terms of molarity. They want me to just say it's moles. so that I'm not making a big deal out of the volume itself. So now we can finally get to what the change was. The change was adding this small volume of strong acid, small because they don't want us worrying about how much room it takes up. We're just going to be dealing with the moles, and we're not going to worry about the volume. We're not going to do molarity. We're doing moles. And it says that we're adding H3O plus ions. So what does that mean? Well, that means that we are going to be shifting this. If I am adding that here, this whole thing's going to go that direction. It wants this to stay small. And yet I'm dumping in 0.015 moles of it. That means it's going to go this direction, and it's going to try to take this right back down to being small enough to not worry about. And the only way it can do that is to take the whole 0.015 moles and shift it over. So the change then is going to be adding the 0.015 here and subtracting the 0.015 there. Equilibrium then will be, when I add these together, 0.165, 0.135, and this is just going to stay small. Now I can go ahead and use the Henderson-Hasselbalch equation and say that the pH should be the pKa of 10.93 plus the logarithm of the conjugate base, 0.135, over the acid, 0.165, and I will end up getting 10.93 minus 0.087. So it is going to be this many units more acidic, right? This is more acidic. So that is what happened to buffer A when you did that. You will note buffer A started at the original 10.93 because these were in balance. Now part B, buffer B is 0.2 moles of methylamine and 0.1 moles of its conjugate acid. All right, we're going to want to turn that one around also, so that we want the acid on the left and the methylamine on the right. So what are we going to do? The same thing we did before. We're going to identify what these are. We're going to say it's reaction. I want CH3NH3 plus. I want the acid on this side with water in an equilibrium with its conjugate base, the methylamine, and the water ends up accepting the extra hydrogen plus. So this is what I want to turn it into. Well, all right, that's fine. What did I have? I had that the pKb was 3.36. In turning it around like this, I ended up finding it as a pKa, which is 14 minus that. So my pKa ends up being 10.64. Fine. Here we have an initial situation. Okay, what's the initial situation? The buffer, it says 0.2 moles of the methylamine and 0.1 moles of its conjugate acid. Well, I've turned this around. So this is the conjugate acid, 0.100. And this is the base, 0.200. Oh my goodness, you know, if I use Henderson-Hasselbalch on this, I'm going to find out that because these are not the same, I am not going to get a pH that's the same as the pKa. My pH is going to be equal to the 10.64, and it's going to be altered by the logarithm of the base over the acid. So the 0.200 over the 0.10 And when I do that, I am going to end up with 10.64 plus 0.301, which is going to be 10.94 when I round it back on the sig figs. So this is the original from the initial conditions. This, of course, is small because that pKa is so small. This is like 10 to the minus 11th. So small compared to these, not worrying about it. Now, what am I doing? I'm doing the usual. I've got to change it. What am I changing it by? I'm adding 0.015 moles of these hydronium ions. If I dump that in here, this is going to do its level best to bring this down to where it's really, really small. So basically, when I throw it in there, everything's going to shift this way. I put in 0.015 moles, it's going to all shift over this way. So plus 0.015 moles here. In order for that to happen, it combines with this, subtracting the 0.015 moles there. This, when you're done, you're trying to do your equilibrium, is still small. This is 0.115. This ends up being 0.185. And now I'm in a position to figure out what the pH is after the addition of the acid. My pH is going to be the original, well, the pKa, right? And now the log of the base, 0.185, over the acid, 0.115. And when I do that, I'm going to get 10.64 plus 0.206, which is, you know, once you account for the significant figures, 10.85. So it is lower. It's more acidic than the original. Well, of course it is. I just got through adding acid. It should be more acidic, right? Now, if we look back at A, all right, if we look back at A, we saw that it also got more acidic, right? But on this one, the change in the amount of acid and the change in the amount of acid here are different. If I look at the change here, it's 0.0. What is that? 9.5, right? Look at the difference between these. 0.301 minus 0.206. That's 0.0. God, that borrow from this. So 9.5, right? If I look at this one, it was a smaller difference. It doesn't seem like that big of a deal. But this one did not change as much. What's the big difference between these two? Well, in buffer A, they were matched exactly. The amount of acid and base were exactly the same to begin with. In buffer B, they were not exactly the same. And buffer B had a harder time maintaining its original pH. And that's what that's all about. It's an example of what we had on the previous slide of the buffer capacity.